大家好，我是王不老，说半岛。Hi, folks. Today I'm going to continue my talks on the packaging process technology with a focus on thermal management of packaging. And then this is a part two. We related to about the thermal stresses. The thermal stresses, TSV pop-ups, warpage, and a discussion of TSMC patterns related to thermal management and simulation tool I'd like to introduce you. So the idea is to present you with plethora of problems and then the solutions and my thoughts on the phenomenon with some basic understanding about thermal stresses. Right. That's the point of this talk. I'm not trying to give you all the details, but hopefully you could use that idea to explore additional content. My, I, as a beginning of talk, I would like to always bring some icebreakers. The icebreaker is a Lego, especially the hardest Lego ever. Somebody in social media summarized the world most difficult Legos. All right, and one of my best friend, who is a avid Lego player, assembled this piece and actually stored it in his cabinet to show off. I always joke about that he could be a good packaging engineer because packaging engineer is about assemble stuff, chips onto a interposer or to a SIP or to a PCB board. It's kind of Lego, isn't it? And but there's a major difference. There's a major difference. Lego has no thermal management issue. It has a mechanical issue because you're assembling two pieces together. They had to be perfectly matched. If you put the wrong pieces of Lego to a construct, then you will see it doesn't work. And then the whole thing will fall apart or cannot be assembled. So that's my attempt to be an icebreaker for you. And if you recall what I mentioned last time, that the thermal stress can induce a warpage. And then you could see that because thermal history and then the residual stress and then the heating and cooling, eventually you will have a Boeing. And this Boeing actually could make material pump out. So in this case, the glue in between to adhere two pieces together because this Boeing and onboarding, this heating and cooling cycle actually eventually act as a pump to pump the material out. Eventually, you know, at the end of the day, it could fail like this. And I also mentioned last time about TSMC. They have a big warpage issue, especially this process called chip on substrate first approach. In this process, what happened is that the substrate is very thin, and they put also a thin die on top. Once they've done that, they find out that there's a huge warpage. Okay, there's a huge warpage, and then eventually causing the yield to be very low. And the warpage happened later at the stage. It's not happening right away. The moment when you bond them, they're fine. But at the later stage, when you're heating up, when you solder them together, the temperature induced thermal stresses, or from the reliability stress test here. The temperature here, we're talking about 150 to 300. And that is enough to cause a huge warpage because these two layers have similar thickness. I'll explain that later. Okay. So this is one of the problem I'd like to show you here about the wafer warpage. There's another interesting phenomenon. I call them TSV pop-up, or people call them TSV pop-up, which means the TSV, the copper via, after the thermal cycle, there are two reasons, the two scenarios of the TSV pop up. They pop it up like this nail. They pop it up, and the reason is the copper and silicons. Their thermal expansion coefficient are huge difference, 6 times. And so that's the reason they pop up. And that brings me to the icebreaker 2, the turn of the screw. We know this is a famous guy, Henry James, wrote this Turner School in the late 19th century. And then talking about some ghost story. It's one of the most famous, beautifully written ghost story ever. Okay, they call it the term of the screw. Gradually turn the screws and get the audience all uh, all angst up in a way that as if the screw is being turned into something. This is just the opposite. The arm turn of the screw, I call it. I try to be funny. Sorry. And here, the via, because the stress, the thermal stress induced at the interface, okay, at the interface everywhere. There's an error here. It doesn't matter. At the end of the day, they all popped up pretty much because of thermal mismatch. And that so how people solve this problem? That there's many interesting way to solve it, but I cast some doubt on that. So this gentleman, Lee, proposed a Spinon PCB liner. So they put a plastic bag, they put a plastic glove around the TCV, around the TSV, and in a way that protect, because it's a rubber, it's kind of a rubber glove, right? So when the strain or the stress here will no longer exist because it's been absorbed by the by the soft liner. Their process that they have this dispensing of the PCB board, and then they do a vacuum treatment to suck out the air inside, so coming in, and then this is typical spin-on dielectric process, SOD, and form a thin layer on the bottom, and this PCB is TSV friendly, so they can deposit copper there. It's an interesting idea, but I don't think it's going to work in SVM environments. All right. The reason is that PCB at the bottom, they cannot get rid of it, right? And suppose you want to, if you have a process, you need to go sideways. Somehow there's another copper line sideways that you need, like RDL or something like that. Then you have a problem, right? You can't do that. And so this is a great idea, I think, but I don't think it's practical. Okay. And there's another way that I saw that's interesting is that let's heat it up. All right. So this thing pop up and then do a CMP. You could remove the excess. Once you remove the excess, the pop-up can be eliminated in a subsequent process flow as long as your subsequent flow, your annealing temperature is lower than the one you apply before this process. So that's the idea. Okay, and that is an interesting one too. But the first temperature you have to use is kind of high. But they propose 400 degrees, right? So this is pretty high for a process because the die don't like this temperature. So this idea is interesting, but I don't think it's practical. You have to reduce the temperature. Once you reduce the temperature, you limit the subsequent annealing temperature. So you put a cap on that. So that's another interesting idea, but I don't think it's going to work. Okay. So All I'm trying to show you here is to show you the power of the thermal stress. And then the magnitude of the thermal stress induced. I would like you to focus on this right-hand table. It's about, here he has a serious case about half a gate, usually about this level, right? And then, so how does this thermal stresses measure and generated, calculated then? We have to come back to this bit. I would like to bring you to the basic, the Stony formula, Mr. Stony, that he figured out that the curvature of a film, if there's a buckle, there's a wafer, if there's the warpage, is calculated by this simple formula. He's using energy balance. That's what he did. All right. It's just using simple energy balance that he relayed the thickness of the film, thickness of the substrate, right? And then the Young's modulus of the substrate, and then the stress induced. He could figure out what is the corresponding curvature, how things bend with this simple formula. And nowadays, people, I would just show you the simple the tool from the web, show you how they actually do it. Right. These two tools I found online, which is very useful, and I would like to share with you. Oh, this is this is Lego. So this is a tool that people use to calculate the wafer wattage. Now the initial bowl of the wafer and the final bowl. So if I change it to say 20, okay, and then substrate thickness of thin film like 2 micron, calculated, right? So you can see that this is the position of wafer, and then the stress level. They show you every detail here. So this is a simple thin film residual stress calculator. May or may not from, by the way, may or may not from the thermal stress. All right, it's just the way to calculate stress, or from the bending, or vice versa. Okay, and that's the interesting one. I think you could play, you know, play by yourself, and to find out the curvature, to find out the warpage versus the stress. And here's another one. This one is interesting as well. I like this one better because I could change the strain, right? You can see that I could change the misfit strain, and then the deposit property in terms of the material property. This is Young's modulus. So that you could play with, and the Poisson ratio, of course, and then substrate property. You could tune it independently, right? And then you could see the change of the property of the material and the thickness. If you change that, oh, okay, good. When you change the thickness of substrate, you can see the thing popped up. And that's this website. I think it's from the University of Cambridge. It's very well designed. I like it. And one of the I'd like to share with you one of the interesting video they show about how do they what's the relationship between the and this one relationship between the especially describing the delaminations, and they have some of the interesting videos. I encourage you to come and take a look at it. It's very educational. Let me show you this one.
Are these stresses important? Initiation of fatigue cracks, erosion, and abrasive wear may all be inhibited by compressive residual stresses, but they can also lead to the spontaneous formation of large sections of coating during spraying, on cooling, or during subsequent service. Residual stresses provide a driving force for spallation because when the coating is detached, released elastic strain energy becomes available to drive crack growth. If the released energy exceeds a critical value, then the coating is expected to debond. This critical value is the toughness of the interface. Using our computer model to simulate the coating of alumina on mild steel, we can calculate how the driving force might vary during spraying and subsequent cooling. Differential thermal contraction during cooling is causing the buildup in stored elastic strain energy. During the corresponding experiment, the alumina coating actually debonded at this point. So we can calculate that for this particular interface, the toughness was about 450 joules per meter squared. Other alumina coatings have been sprayed under different conditions. The modeling work shows that all of them debonded at similar values of the interfacial toughness, convincing evidence that it's possible to measure this property.
Right, that's one of the videos from the web. I think it's very educational. Please take a look at it. If you have time. My question for you is that if you see a wafer warpage, does it mean that it is caused by thermal stress? Right, you see some of the wafer warpage, oh, the thermal stress, and then because it went through the very high temperature, and you cool it down. But my answer is that that's a big no. Because when you deposit, I especially focus on CVD process, all right? When you deposit, let's say CVD thin film, SiO2 on your device, they have huge stress. The reason is simple, that if you have too many atoms that pack into the film, bond lengths are pushed shorter than normal. The film tries to relax back to its normal bond strength, pushing outward and forcing a convex. Here is a convex, okay, the compressive one. A convex compressive stress curvature of the wafer. On the other hand, if you deposit too few atoms, then the tensile is not enough. So they want to bond them together, right? I'm just exaggerating. You have two atoms, and then they want to bond together. If too few together, then they will bring the substrate with them because the bonding strength is huge. So we're talking about the bonding strength. And then the calculation of the film stress here, done by the simple formula here. Okay, it turns out that the thin film formed by a CVD process, it's usually a large compressor on the wafer, and usually around gigapascal. Okay, this is what's measured later on. And thermal stress is usually way smaller. Okay, let me show you one example. Say, this is, if you go measure the tungsten depth, you will see gigapascal compressive stress very easily. Any CVD process, pretty much. But if you look at an extreme example of a thermal stress. The thermal stress generated from SiO2 formation on silicon wafer will push it to about 1100 C in oxygen or moisture or H2O before cooling down to room temperature. Right? Then we would like to calculate what is the thermal stress from this thermal history. The silicon wafer elongated when heating up to 1100, right? That's everything elongated at high temperature. It's just different degree of elongation. Silicon will move sideways, or expand 1 millimeter. But the SiO2 form on top can only do 20% of that. And that the difference between these two create, the stress. That is a real thermal stress. That's the Young's modulus times the temperature difference times the thermal the thermal expansion coefficient difference. So you put this together and you figure, wow, it's only 0.18 gigapascal. It's reasonably big, okay? Don't get me wrong, it's still big. But if you compare with a thin film stress from a CBD process that you go measure in your flow, you can easily see gigapascal on your from the stress measurement. So that's the reason I said thermal stress is usually way smaller compared with the intrinsic stress that induced by the bonding. Okay, in this case, in this specific case, this wafer the wafer warpage is caused by these depositions of this overly dense material or under filled not enough deposit. So this is not enough deposit. This is over, and that is very different. So when you see the wafer warpage, here is purely done by thermal stress. Okay, it's not by deposition because there's no deposition. But when you see a wafer bending, please don't confuse this one with the packaging, the wafer, the thermal stress in the packaging world. This is in the CVD world. You know, this curvature, this bending is caused by the CVD bonding strengths, different bonding strengths history. So this one, the big difference I like to make it, hopefully can make it clear to you. And if you see that the case I presented here about SiO2 formation, and usually if it's done right, if the SiO2 is not too thick, you have a porosity formation because SiO2 is soft compared with silicon. The Young's modulus of SiO2 is about half. All right, it's about half of the silicon. And in some case, if you go too thick, then you start to generate micro crack. Or sometimes the temperature very high, as you have viscous flow, because SiO2 is kind of like a plastic, so you have a viscous flow. Actually, these are all very important in semiconductor process. Okay, the viscous flow is when you heat out the wafer to very high temperature with SiO2 as interface. That is critical to make the device very reliable. All right, you have to have a viscous flow happening in a way that you arrange its atom in a way to reduce the interface defect here. Okay, that's in other talk I have. But this formula, this Stone's formula, the Stony formula that I mentioned here, has been modified ever since, especially this nonlinear deformation or larger wafer size with multi-layers. These things get more and more complicated, right? So they have to modify the formula to variety of formulas that people derive to fit their special needs. So this is one that be modified. This is just an FYI. Say that don't rely on a simple Stony formula. If you have a multi-layer, one on top of each other, and that changes the history, not changes history, but change the basic assumption of Stony, how he derived his formula. Overall, it's still energy balance. Okay, the energy balance of all the three here that eventually they will have different warpage with the multi-layer on top, and that you need to analyze and or find a paper that describe what's happening. Then my question for you is that why the chip-on substrate first is prone to have large warpage? Okay, that's one I described previously here. That's because when a chip is placed on a thin down substrate, any residual stress induced is shared by the two with a percentage proportional to the inverse of thickness. This is pretty much the key concept I introduced. Because the strain, if you have a very large, very thick substrate, then the substrate doesn't feel anything. Even if you have a very thick substrate, imagine your big earth, and then there's a coating on the earth that's very so thin. The earth doesn't feel it. Okay, it doesn't feel it. But if you have a thin layer of thin film that deposit on a thin substrate, like the one I'm showing here, okay, magnitude is about the same, especially if this layer is like say 10 micron, or this is 10 micron and this is 20 micron. They are comparable in thickness. Then both have to share the strain properly, and that the it will cause, if you have because energy has go down to the thin substrate as well, so it will have a larger bending, a larger warpage. If this is infinitely thick, all right, then it will be no. If your substrate is so thick, say 375 micron for typical wafers, or even 700, then itself doesn't feel that much. All right. So if you have some strain, say from this one, okay, only a couple megapascal, right? Here, give you an example here. If you have strain is in this range, okay, or even smaller, right? These are extreme cases, okay. Then the warpage is going to be very small, because the energy coming into this thick substrate is very little. All right, so it doesn't bend. Overall, it doesn't bend. Now, if for the COS process, the chip-on substrate process, the substrate has been thinned down. So here, it's been thinned down tremendously. Therefore, the energy go down, the strain energy go down to the substrate a lot. Therefore, it bends. Okay, so that's that eventually substrate will warp easily if its thickness is close to what the chip thickness. So that's why this process has been dropped. The yield loss is too large, right? And later on, let's look at if you recall, the micro fluidic heat sink process that demonstrated by TSMC. That they try to reduce they try to cool these wafers. Okay, they try to cool these wafers, and with fluid pumping through. There are two ways of doing that, with a liquid cooling and then direct cooling. And then I think all these special architecture design are their patents. Sorry to break into this topic, segue to this topic quickly without going back to the warpage. I just want to emphasize the warpage topic is over now. As going down to this is kind of heating issue, and we're going to the cooling issue. Okay, how do you cool the wafers so as they don't really have a big problem of take the heat out without having a warpage issue. Okay, and I introduced this one last time. That is paper from the TSMC 2021. They have a two-way of cooling it with different way of with the cover and the lid, or just cover. And if you look at their patterns, in this pattern, they have a heat dissipation rings and lids. Okay, so they have a pattern around it. So this way, when they publish a paper, they have pattern to protect that, because otherwise people learn, because once you become a paper, everybody can copy and paste and do it themselves if you don't have any patents. So the patent will come before the paper, so as that people look at what you did and they become a copycat, and you cannot forbid them to do anything, right? So without the patent. So this is a patent that I found that I think is really relevant. So they have this heat dissipation rings and lids. And they have high thermal conductivity and is attached to the component, right? So they have with some kind of the thermal interface material. We discussed that the Mr. Tim, and then all these different architecture is similar to what I saw here in these published papers. Okay. And this is, I think, the most relevant paper pattern for the paper I just showed. And they have another paper about cooling. This one interests me because they talk about the cooling, the passive cooling. All these are passive cooling, by the way. Okay. They still believe that passive cooling, no matter how well you design, is still problematic because you don't know where is the local hotspots. Right? It's a passive mode, right? Running water through it or heat sink above it. It's always passive. Even microchannel cooling as here. Okay. This is microchannel cooling. Right? You could divert water here and there and try to cool it. It's still kind of to this inventor, it's still kind of passive. And it could have a fluid leakage. All right. So all these are bad things. You imagine if you do it, if any in this package, if you any pillar that is designed or from a process, so any water coming into your packaging, you're dead. Right. So it put a huge challenge on the control of these methods, and whether they're going to be SBN compatible. You've done a lot of experiments to make sure that the water will not attack your devices, right? So they propose a thermoelectric cooler for actively cooling over 3D IC. I think that's a great idea. That's really a fantastic idea. You can selectively cool where you want to be. And whether you can do it, I don't know. But at least that idea is great. So that's the reason I mentioned it. And it's easy to find quite a few TSMC patterns on cooling or heating or heating control of 3D IC, but not so much from Intel or Samsung. Okay, so they because I think TSMC focus a lot on this area, so they have many more patterns than the other two. Okay, then let's conclude this FJ system with this picture. All right, you can look at that. The cooling, they actually have additional steps, additional architectures. Here we have this conductive silicon lid. All right, these heat conductors been placed properly inside this structure. And if you put everything together, you see that actually you have to have the thermal bridges, right? So this heat spreader, okay. And then this the cooling, the heat sinks, and there are additional heat sink, auxiliary heat sinks. And then the air gap, here is the air gap, okay. The air gap isolation, so as the heat generated by the logic processor will not directly affect the memory cube above. This is one example. You put memory which is not heating up at all, and then the processor heating up all the time together. You want to separate them with some kind of air gap. These are great ideas, but whether they can do it, that remains to be seen, right? Because you have to create the air gap, which is not a simple process, by the way. The CMOS world try to put an air gap that Intel 10 nanometer, they have IoT zero gap, and they did it only once. I don't know whether they have the HVM on that or not. But at least I'd like to show you what are the ideas in the overall MF HS the all systems. What they should have. They should have heat spreaders, thermal bridges, air gap. If this is a comprehensive one, all right. Whether you could do any part of it, that remained to be seen. You had a demo with the with your customers, right? So, but this idea is there for you to use. Okay, and here I'd like to show you that the thermal problem with two-tier 3D IC. This is the typical famous monolithic 3D IC, and this is a TSV-based 3D IC. All right. The major difference is here. Tier 0, Tier 1 are two different dies, and they bound together by this IOD process. And here is done by TSV process. A bonding layer, very thin. On the left-hand side, it's about 100 nanometer SiO2. And then the bonding layer here is quite thick, is about 33 micron. So I would like to challenge you, what are the key thermal issues that you see from this 3D IC? What happens if something heat up? Which one will give you the worst case? Well, the answer is very simple, right? This one give you a very bad thermal issue. Why is that? Because it has one to conduct the heat away. All right, you could do this and do bottom, depend if you have anything. And here, the only thing that conduct the heat away is the handle bulk 75 micron, same as here. But they also need to conduct the heat away sideways, right? Because heat has no heat is isotropic. Heat transfer is isotropic. It goes everywhere. And how do you transfer heat sideways? Here's SiO2 is the insulator. So there's no way you can heat it's very difficult to transfer your heat outside, sideways. Here is just normal. And in this way, in this one, of course, this one is the same in terms of the y directions. They going through, but there's a strong path for going heat sideways, right? Because the die structure, everything here, bond layer, if you use a heat conductor well, then you could always conduct heat sideways. So the cooling of tier 01 is much easier than the tier 0 on the left-hand side. So, but what's the problem? Why people go here this way then? And because they look at the vias, the TSV is large, and here you could get very small. So this can be made very high interconnect densities, and here you cannot. So that's a major difference. So they all have a pros and cons. This one, because TSV is thick, right? This is a thick copper wire, and so he can conduct this way easily. And here, difficult. Because heat very difficult. So if you have generating heat here, it cannot go sideways because it's been blocked by the insulator, and it cannot go upway because the VR here is very small compared with the right-hand side. So this one, the temperature of this one will be super large. Okay, super large. And here one is reasonably. Okay, so I'd like to share with you, just looking at the picture with some simple fundamental knowledge of materials, you could easily see that the thermal stress and thermal issues of these monolithic 3D ICs with MIV is much worse than the TSV one. Okay. Then, well, all these fancy stuff that I introduced you, at the end of the day, you need to put into a simulation tool. Okay. Here I'll show you two. One is the ANSYS one is Cadence, the Celsius solver. And both try to simulate thermal stress analysis. Okay. And I hope if you have time, take it into their website, or you can play with the software to show exactly how it works. Okay. Let's look at one of the Cadence Celsius thermal solver that how can you use this software to simulate your packaging thermal electric performance and behavior? All right, this is just one of the picture I took from the website, the electrothermal code simulation. So because what we shown here are basic thermal ideas, but in reality, the devices are working, right? Some are hotter and some are in some spots are harder than the other because, like logic, they're much harder than the memory because that's the way it works. You have more current inside. Then the software these days can take care of this problem. And let's look at the Cadence Celsius thermal solver.
System. It's to accurately assess the thermal reliability of your system. It's important to ensure that components function according to their thermal specification. The Celsius thermal solver makes it easy to measure and evaluate thermal profiles anywhere within your system, all the way from the enclosure to the logic cells inside an IC. Utilize the integrated CFD and FEA solvers to analyze heat transfer or run an electrical thermal co-simulation on your entire system for accurate temperature measurements. And solve large 3D structures 10 times faster than legacy tools without compromising on accuracy with distributed computing and massively parallel processing. The integration between the Voltus IC power integrity solution makes chip thermal optimization easy, as you can evaluate the power profile and temperature variations on IC packages. With the Celsius thermal solver, you can accurately model and analyze the thermal and power integrity for chip, package, and board designs.
Okay, folks, I think I've been introduced enough. Today, my focus on the part two of the thermal management, talking about thermal stresses compared with the intrinsic stresses from CVD, and that are very different, although they could show the same warpage phenomenon. And then the TSV pop-ups, and then TSMC patterns, and the Celsius thermal solver for you. Hope you can appreciate it. Okay, that'll be all for today.